very complementary to the code expansion over there. So let me summarize this at the diagrammatic level. Again, the Walsh diagram first of all contains the primary diagrams of the master's field theory, referring to the Yang-Mills tree you have factored out. And now, each of these additional alpha prime terms can be interpreted as a new vertex. So for instance, that guy can be viewed as coming from a 4-point direction vertex. And if you do a careful counting, there are 4 derivatives and 2 alpha primes hidden in these matter stubs. So accordingly, this effective vertex must be of the order f to the 4, 4 powers of the Yuan field strength. Produce all the derivatives seen over there. And accordingly, the next term with the zeta 3 has 3 powers of alpha prime and 6 derivatives. Now, in gauge covariant language, this again corresponds to 4 powers of the Yuan field strength plus 2 more derivatives. Extra 2 sitting in the third minus one. Okay, how does this relate to the infinitely many states we have probed in the previous expansion channel, expansion method? Here, in this power series expansion, we pretend that the massive states are integrated out. So you can think of this f to the 4th and d squared f to the 4th guy as effective vertices from integrating out massive nodes. Okay, so this concludes the opening, motivating part of this lecture. I just wanted to start by giving a flavor what kind of regimes are interesting about string amplitudes, and I will now proceed in a more organized and systematic way, and in particular give you more details of how to perform the calculations in full flow. The outline goes as follows. We will start looking at the open bosonic string at tree level. Stand some Luhmann amplitudes there, but we will very early stage realize that there are some unpleasant properties in the bosonic string, and that it will be easier to instead discuss the open superstring. We will see how Gaussian supersymmetry is our friend to simplify the amplitudes. So this will probably be the main body of the lecture. I'll also report on the recent results on the endpoint treated amplitude, talk about the structure of the integrals defined, how you recover various symmetry patterns from the field theory, such as Weiss-Coy and BCJ relations, how the integrals they relate to the formalism of the list. So all of this will happen in part 2. Then certainly I should also cover the closed superstring. Give you the famous KRT relations. And then hopefully there will be time left to discuss some advanced topics. So this will be a collection of things that are currently happening on the research frontier, ranging from alpha prime expansions, further loop amplitudes, to spinor formalism, to quantize the superstring in a manifestly supersymmetric manner. So all of this are hopefully covered tomorrow. Okay, let's now jump into the bosonic string part. Let me start with the Welch action. Build up the machinery which is involved in the computation of bosonic string tree level amplitudes. We will parameterize the Welch worldsheet using a complex coordinate. And the worldsheet mathematic short sigma. And we start by postulating the following worldsheet action. Integral over the worldsheet. Now the position of the string in space-time is regarded as a worldsheet. So here this xn simply tells you at which point in space-time the worldsheet is sitting. And here I'm summing over vector index of the Lorentz group and knowing 0, 1 all the way up to d minus 1, where d is the dimension of space-time. So how can we motivate this, or what can we say about that? In a certain sense, this is a generalization of the world dimension. For a point particle, you can describe its free motion by minimizing the world dimension, which is nothing but the length of the world line. And since the worldsheet just generalizes the world line, here this action is useful to think of as a certain version of the area, the worldsheet area, as the generalization of the world line length. But it doesn't really look like an area, and in fact, there are a couple of things that you have to do to connect it with an area. So let me just say it morally corresponds to the area. It's the gauge-fixed version. There are many things happening in the background which you can find in string theory textbooks, like first introducing a metric of the worldsheet and doing some sort of general relativity in 2 dimensions. And then you can recognize a lot of gauge freedom. At the end of the day, you fix the worldsheet metric in such a way that you land in this gauge fixed action, which we will use in the following. What is nice to observe is that this action has a symmetry. It is conformally invariant. If I send with coordinate z to some holomorphic function of z, and I can at the same time take the complex conjugate z bar, and even pretend that the complex conjugate was independent, and reparameterize both z and z bar separately. Okay. Holomorphic and anti-holomorphic function respectively. So this is a symmetry of this worldsheet action here, and if you're not careful, there will be an anomaly. Unless you are careful about the space-time dimension. There's a anomaly for this conformal symmetry unless you choose the dimensionality of space-time to be 26 bosonic string. So it's a nice feature of string theory. It predicts the dimensionality of the space-time it likes to live in. And the corresponding number for the superstring is e equal 10. We will now use this action to define correlation functions. Correlation functions of certain worldsheet fields that model the external state insertions. But before going to the state insertions, let me just do this exercise abstractly of computing correlation functions. So, whenever you're given an action and asked to compute correlation functions, the central question will be, what is the kinetic operator and what's its inverse? The inverse of the kinetic operator, the inverse of which Green's function do I have to take such that this operator produces a delta function? And the answer is the logarithm, two dimensions. That's the Green's function for the two-dimensional cluster. And we reduce normalization units. There are a factor of -2 alpha prime comes along the way, along with the Minkowski method to reflect vector indices. Okay, given that this is a quadratic action, a free theory, it's now very straightforward to compute correlation functions. We just employ various big contractions. And one of the central ingredients between amplitudes, that's the correlation function of many such plane waves. So this plane wave factor will generate space-time and momentum in the worldsheet. And suppose this was the end of the story. Suppose I would take nothing else for the state insertion. Then this gives rise to the following correlation function. You can pull all the contractions into the exponent. And as a result, you get all the differences of the insertion points weighted to the power of a dimensionless undersigned pair. So here, remember, this SIJ is defined here, essentially a dot product of the momentum with the factor of alpha prime to make things dimensionless. So it's perfectly legal as a dimensionless exponent. And what you also get is a momentum conserving delta function. This essentially comes from the zero mode part of the path integral. And to be honest, this is often, well, not explicitly tracked. I think I should also have inserted the delta function here. So let me already announce the abuse of notation right here that we won't take this delta function along all the time. You certainly know that it's there. Okay, but as I said, this is a very important object, so let me therefore introduce a notation for it. Since we will use it zillions of times. For this product of all differences, I will use the notation capital I and refer to it as the so-called covariance factor. As you will see, this is really the engine of treated amplitudes, or also the new amplitudes. For instance, it specializes to these ingredients of the ball-line amplitude, which later on generate the poles or the effective vertices in the alpha prime expansion. So you will see this over and over again. Now to finish off the correlation function part. In the context of muon scattering, you will also meet correlation functions where additional insertions of this type here, the field x not inside the exponent, but just outside in the form of a z derivative. And by the link rules, you can evaluate those correlators recursively. First of all, the covariance factor always factors out. Now there are generically two kinds of contributions, depending on how you do your big contractions. One type of contraction goes across the x field, that will produce stuff like the Minkowski metric along with a double pole. end, you can iterate this procedure to compute two correlation functions of arbitrary length, arbitrary numbers of such dx instructions. That's all we need to address the gluon. So let me now introduce the gluon vertex operators. And as a general statement, before commenting on the gluon, the way how you insert an arbitrary state to a string worldsheet, you need a conformally invariant deformation of the action. So the emphasis is on the conformally invariant. Everything that preserves conformal symmetry has some meaning inside string theory. And a particular class of conformal invariants is if you take an integral over the boundary of the worldsheet. I mean, this really corresponds to docking on an open string state to something like that. And every worldsheet field defined which keeps this guy invariant is an admissible state. That's basically the rule how to construct the spectrum. And I'll just give the expression for the master's open string states at that point. I'll drop further subscripts here. I'll just use the index j to refer to the j one. And now the simplest, or the only master's vertex operator on Masonic string theory is to take some vector, epsilon, contract into the field S. And decorate the framework. And to make sure that it really forms a conformal invariant, you have to demand that the momentum squares to 0. So the mass distance of the gluon comes, if you wish, from the conformal invariants which we impose. And on top of that, you need a vanishing dot product between the polarization vector here and the mass's momentum. So also transversality is a consequence of imposing conformal invariants. Now that we are in the middle of discussing the degrees of freedom of the gluon polarization, let me make a comment about a gauge transformation in linearized form. Under a linearized gauge transformation, where you replace the polarization by its momentum, which certainly preserves the transversality, it turns out that the vertex operator then becomes a total derivative. Imagine this is Kn, then in that limit you can regard this as descending from taking a total derivative of the exponential. And this is a good point to state the general rule of thumb in string theory. Boundary terms integrate to 0, at least when it's about a boundary term with respect to the worldsheet position Z. Let me back up this broad claim. Why do total derivatives decouple? Or why does this one decouple? this integral along the logic boundary will always be bounded by some neighboring state instructions. So going to the boundary means that you will eventually evaluate the correlation function at collision points. So this is how a typical boundary term looks like, or this is what they are proportional to. Remember here I'm using the shorthand for the probability factor. So this IN is just a product of many such guys. And how does it behave when ZA collides with ZB? Something that goes to 0 raised to the power SAB. Well, I haven't told you about which kinematic regime we are, but let's for the moment assume that SAB has a positive real part, then this is a really obvious statement. Something raised to a power of the positive real part is 0 in that limit. And in different kinematic regimes, one can save the day by doing a proper analytic continuation for generic kinematic points SAB. So we won't restrict the range of the excited cases. Okay, so as such, this derivative really decouples also at the practical level. And here, this is a first point to make contact with the scattering equations. Let's look at the particular total derivative which you get by differentiating the covariance factor. Under integration, any such derivative of the covariance factor couples if you look at its explicit form, if I differentiate with respect to any of the Worldsheet punctures, say the 8th one, what I get is that guy. Each of the factors where the chosen ZA is contained will react, will respond to the differential operator, and therefore builds up this sum here, which you have seen plenty of times in Alice lecture. So, in that sense, also string theory wants that these sums here become. Certainly there can be additional dependencies on ZA which could obstruct the direct application of that rule, and I'll give you an example shortly. This example will be within the 4.3 amplitude. In order to get there, let me state the general description. For n non-trivial amplitudes in the bosonic string context. So my notation is subscript was to indicate that we are in this rather dangerous zone of the bosonic string, while later for the superstring on the ground. Okay, we'll do a color product and particle scattering, remembering that there is a trace of color factors pulled out. And the way how this is computed, we take plenty of these conformally invariant state insertions for B being the vertex operator of the neuron. structure of neighbors goes like that. And this must be reflected in the integration region. Let's parameterize this according to a real coordinate. And let's put the point at infinity, say between particles 1 and n. Then I must make sure that C2 has a real number. It's larger than C1. So like this, you get an iterated integral over these guys. And at this point, you could complain that I'm handing you a badly divergent quantity. Namely, I've emphasized that we need this conformal invariance, and as such, there are many configurations which are badly overcounted by this conformal invariance. We have to fix the freedom of performing conformal transformations of the integrands and punctures. And like in this lecture, the conformal transformations can be described by an SL2 matrix. Alpha, beta, gamma, delta, which has a unit determinant. So according to the 3 degrees of freedom in that SL2, I have to drop 3 of the integrals. So like Alice did it, I have to divide out by the volume of SL2R. And this is done as follows. You drop 3 integrations. And it's up to you which ones you drop. You can choose any 3, A, B, and C, where you do not perform an integral, but then you have to make sure that you preserve the scaling, the SL2 scaling of this particular function. So you must introduce this Jacobian, which can also be motivated as a correlation function, so world-sheet posts. Okay, so this prescription here fixes the leftover conformal transformations, and then you can arrive at a well-defined integral expression. Here, for convenience, I don't like to integrate all the way up to infinity. So in order to confine the integrals to the unit